Good morning, one and all. So we are starting uh, 20th lecture. So in this subject, generally we are given 40 lectures to complete all the 5 modules. We are doing 20th lecture today, and we can say that we are in the halfway stage of this module. So 2 modules are already completed, and today we will complete till the half of the third module. So the third module is mainly talking about different energy generation elements. So electrochemical battery we have seen, that was one energy generation element, and then today we are going to talk about ultracapacitor. So let me change this. So this is battery specifications, and also this I will change. Today's topic is ultracapacitor. Still students are joining, so we can afford to start at 10:05. So today's topic is ultracapacitor, and it is a capacitor which is charged till the extent maximum possible thing, maximum possible charge, and then we can get the supply from there. So whatever charge is stored in the ultracapacitor, later on that is used as a voltage source or power source. Now, what is the difference between battery and ultracapacitor? So, battery is mainly used as a voltage source or energy source. Rather, voltage source, we should say it's used as an energy source. But ultracapacitor is used as a mainly power source. So, difference between energy. So, energy is given in joule, and energy per time, that is actually given by power. So, how fast you want the energy to be delivered. So in that case, we have found that battery is mainly an energy source. So we can get energy from there. But if we want very fast energy from some device or some charge stored element, in that case, battery discharge is not very fast, what we find compared to ultracapacitor. So ultracapacitor is kind of a power source, and battery is a energy source. So ultracapacitor construction, we will see what are the features of ultracapacitor. We will see what is the functionality, what is the mathematical model or circuit schematic model of ultracapacitor, that also we will see. And finally we will see what are the different technologies in the field of ultracapacitor. So in battery also, last day we had seen there are different technologies like lead acid battery, lithium related battery, so LiP, Li, there are 2 batteries, there were different types of nickel batteries, all those things we have seen yesterday. So today what we are going to see is ultracapacitors. You can see here. So features, operating principle, obviously construction will be there. Construction is little different than capacitor, but almost similar to a capacitor. But there are very specific differences, we will talk about that. Performance of different ultracapacitor technologies. All these things we will find in the module number 5, sorry, module number 13, page number 356. At the end of the battery, one very important topic is pending, that is battery management system. And what I'll do today is I'll upload the ultracapacitor lecture, whatever is being conducted now. And after that, I will upload all the links related to battery management system. So 5 or 6 links I will upload. You see all those links. So there is a 3 lecture series in battery management system that you see. So there are 5-6 links I will upload. You see all those links. After that, by next week, early next week, I will record a session and I'll upload. So after you go through all the links uploaded for battery management system, so how to charge the battery, how to get the best performance extracted from the battery, all those things are discussed in battery management system. So this is nothing but the embedded system side of the battery technology. So it is about battery management, how well we can use the battery, how well we can extract the best performance from the battery, how well we can track or sense how much is the charge stored in the battery, and all those things are explained in the battery management system. So every vehicle is having a battery management system, whichever vehicle is driven or controlled by a microcontroller, there is a battery management system. And this Tesla and all these things, whichever are electrical driven car, definitely there are battery management systems, and huge amount of research is being conducted in BMS. And this kind of research requires in-depth knowledge of control system, embedded system, electrical or electronic hardware, software, and there are a lot of different kinds of adaptive controller and other controller technologies which are also required in battery management system. And battery management system is there for vehicle. The same system is there for satellites also. The same system is there for missiles. So everywhere there is a battery management system. Wherever we are using battery, there has to be a smart management. So this topic I have skipped intentionally because I want you to go through first, and after you go through all the 5 6 slides, so together it might be around 1 1.5 hour session. All those 5 6 links if you go through. Finally, I will conduct the session by next week. So today we are going to do ultra capacitor. So enough students have joined. 23 we are having. So officially I am starting. Okay, so good morning, one and all. We are going to see the ultra capacitor topic today. So this is in the module 3. This is lecture number 20, and this is 1st May. So we are going to we are almost at the halfway stage of the syllabus. So if we complete this, the third module also will be completed half. So what all topics we are going to see in ultracapacitor, that is features, operating principle, performance, different ultracapacitor technologies, and we can find it in the book of Ehsani, module number 13, page number 356 onwards. What is ultracapacitor? So first we should know what is ultracapacitor, then we'll see the feature, then its construction. So construction of ultracapacitor is not same as the simple capacitor. So ultracapacitor is a charge storing device which we charge it first, we store some energy in the ultracapacitor, and then whenever required we connect it as a voltage source and we discharge the ultracapacitor through the load gets some power. Okay, so battery is a energy storing device, and ultracapacitor actually delivers power. So whenever we want energy from some source we use battery, whenever we want power from such source we use ultracapacitor. So frequent start and stop operation of EV and HEV requires highly varying discharging and charging profile of the energy storage device. So there is not only energy, then there is not only energy supply, but energy supplied per time. That is what is talked here. That electric vehicle or any vehicle, you can say, if there is huge traffic ahead, you have to do start stop, all those things continuously. It has to be done, and it actually creates a lot of pressure on the battery. Okay, suddenly it is working in the full 100% efficiency, and suddenly it has to stop to zero, again start, again stop. So we have seen if there is an inductor at the load, and there is a DC chopper kind of configuration we have seen in flyback diode or freewheeling diode. Suddenly if you are stopping the power supply, what happens is a huge amount of negative voltage is produced in the motor, and that actually comes back and hurts the semiconductor switch and the diode. Okay, so sudden stop actually gives some shock to the circuit. So battery also it creates some shock. So to absorb that shock, what we are doing is, in case of electrical circuit, we have connected a freewheeling diode or flyback diode. So any system, whenever we are starting it, whenever we are stopping it, it should be done gradually. Sudden start stop, as we find in case of vehicles, it actually requires highly varying discharging and charging profile, and it is a little difficult for the battery to satisfy that very highly frequent starting and stopping. That is a problem in case of battery. But another few more things are written, that average power required from the energy storage device is much lower, okay, than the peak power requirement. So when is peak power requirement? Whenever we are climbing hill, okay, at that time heavy amount of power is required from the battery, or whenever we are starting the vehicle at cold cranking, that means temperature outside is around minus 25 degrees centigrade, and we are supposed to start the vehicle. So at that time huge amount of power is required. Okay, same thing happens in case of aeroplane also. Whenever the aeroplane takes the flight, it is trying to fly, so take off. At that time, huge amount of power is required. At that time, we are asked to switch off all our also all light, this, that, everything, whatever are the things that we can use inside the aeroplane, everything is shut down at that time, because all the power is concentrated to the energy. So when the plane goes up at that time, again, so just to drive the aeroplane, it does not take much power, but take off at that time, huge amount of power is required. So same thing, that is actually peak power. Whenever we are climbing a hill by a car, at that time peak power is required. So average power required when the car is on a smooth road, plain road, flat road, on a highway or something. So driving the car on highway is very easy because it is flat road. Banking is not there, that means inclination is not there much. Okay, we just have to hold the steering and keep on pressing the accelerator, that's all. And we should not sleep, that is another problem. Okay, but peak power requirement is too much. So whenever sudden jerk comes, hill is there, all those things, at the time main power is required or energy is required from the energy supplying device. So peak power is required for sudden acceleration. That is another thing. So suddenly, if acceleration is to be done, so suddenly the battery has to supply peak power. So all this we are talking about in case of electrical vehicle. It is not petrol or diesel engine. It is electrical vehicle totally driven by battery. Okay. So in that case, we need sudden energy in a very small period of time. So whenever this period thing is coming, whenever this time thing is coming, that energy has to be supplied within a very small time period. There, battery actually is falling short. So the ratio of peak power to average power, you can find 10 as to 1. That means if for driving on the highway, we need 10 units of power. For hill climbing, we need 100 unit of power or energy. Okay, so in HEV design, the peak power capacity of the energy storage is more important than its energy capacity and usually constrains its size reduction. So one is energy delivery and another is power delivery. Power delivery means energy delivery in a certain period of time, a short period of time. So battery is falling short there. So battery can give huge amount of energy over 20 hours of time. Battery can give you a lot of energy, but in very small period of time, maybe in 3 seconds, maybe in 1 minute. Okay, you are asking huge amount of energy from the battery, and battery is unable to supply that. So there is coming the use of ultracapacitor. So ultracapacitor, you have to remember, is for power delivery. Battery is for energy delivery. And energy and power differences, whenever in short span of time we need huge energy, actually we are asking for more power from the device. So based on the present battery technology, battery design must make a trade-off among specific energy, specific power and life cycle. What happens if you are extracting or if you are trying to extract huge amount of energy from battery within a short span of time? So battery can give huge amount of energy, but over a stretched period, not in very short span of time. But then also you are stretching the battery. Okay, so I give you an assignment, I ask you, very big assignment I give you. So that is assignment size is proportional to the energy. So huge big amount assignment I give you, and I give you 1 month's time. So every day you do little bit and you complete the assignment over 1 month's time and you submit, no problem. But that huge amount of assignment if I give you and I ask you, why 3 दिन में submit करो, so at that time it will stress you people. Okay, and that stress on battery, that is huge amount of energy if asked from the battery within a very short span of time. In that case, the battery might crumble. Okay, it might supply, sometimes it might pull it through, but too much of exertion within short span of time might damage the battery characteristics or battery health. Okay, so life cycle is a very important thing, that if battery health is getting damaged, that battery cannot be used for more number of periods. So we cannot expect huge amount of power from battery, but huge amount of power can be expected from ultracapacitor. So difficulty in simultaneously obtaining high values of specific energy and specific power. So no device is there which can give high specific energy and high specific power. Battery can give high specific energy. Ultracapacitor can give high specific power. That means huge energy in short span of time. And life cycle has led to some suggestions that the energy storage system of EV and HEV should be a hybridization of energy source and power source. So battery is an energy source, ultracapacitor is a power source. Energy source, mainly batteries, fuel cell, has high specific energy, whereas the power source has high specific power. Power means energy per time. So power source means which can give us huge amount of energy in short period of time. So power sources can be recharged from the energy source during less demanding driving or regenerative braking. This is a very important thing. That is, we are charging the power source. Ultracapacitor can be charged from the energy source. So from the battery, the ultracapacitor can be charged in less demanding driving or regenerative braking. So in the previous slide, one thing, very important thing I had shown you, that peak power is to normal power. That ratio is 10 as to 1. So whenever the vehicle is running with normal power, it can generate 10 unit of power, but it is requiring only 1 unit of power for driving. Hence, where is the 9 unit of power being used? So in that case, some energy can be used to charge the ultracapacitor. So that is a very important thing we are talking about. So during the average or normal or nominal running condition, the battery can charge the ultracapacitor. The battery is a specific high specific energy device, and ultracapacitor is a high specific power device. So the power source that has received wide attention nowadays is the ultracapacitor. So this is why ultracapacitor. So that question can be asked. If it is asked from these two slides, you can find the answer. Every slide is important, so I have put two star in every slide because it's a capacitor and it's in our domain. We can understand. So ultracapacitor is characterized by a much higher specific power, but much lower specific energy compared to the battery. So over huge amount of period, if you are asking huge amount of energy from the ultracapacitor, no, you cannot get it. But within a very short span of time, if you want a huge amount of energy, ultracapacitor can supply that. So its specific energy is in few watt hour per kg. Few watt hour per kg, 4 watt hour, 5 watt hour, 10 watt hour, likewise. Its specific power can reach up to 3 kilowatt per kg. So 3 kilowatt, okay, that means 3000 watt. Whereas its energy is specific energy is less. So watt hour is the unit of energy per kg, and watt is the unit of power per kg. Okay, so specific power. So these are the small details you should remember. Specific power can go up to 3 kilowatt per kg, much higher than any type of battery. Due to the low specific energy density and dependence on terminal voltage on the SOC. So SOC and terminal voltage, they are heavily related in case of ultracapacitor. We will see the graph. It is difficult to use ultracapacitor alone as an energy storage for EV and HEV. So we have seen in the Hindi movies, all the heroes are having a sidekick. So there is a side hero, as we call it. So ultracapacitor is the side hero. Okay, they will not come in action every time. So hero will do the main act throughout, but there are some critical moment. There are some peak demand at that time. This ultracapacitor will come into use. It will do its job small. Again, it will go out. So it's dependent. It's not the main power source. So only ultracapacitor is running the vehicle. Not possible. It is not possible. Okay. So battery will be running the vehicle, but some cases hill climbing, maybe acceleration, sudden acceleration. In those cases, we might hybridize the ultracapacitor with the battery. So this is a very important line. Due to the low specific energy density and dependence on terminal voltage on the SOC, it is difficult to use ultracapacitor alone as an energy storage for EV and HEV. So this is a sidekick. This is a ancillary kind of a supply. So battery plus ultracapacitor can be the best choice. Nevertheless, there are several advantages that can result from using ultracapacitor as an auxiliary power source. Just see, that is not the main power source, but it's auxiliary power source. One promising application is the so-called battery and ultracapacitor hybrid energy storage system for EV and HV. So already we have explained this, that during normal running condition, we are going to use high specific energy wala battery, and in peak period we are going to take the power from auxiliary source like ultracapacitor, which is having its specific power in the range of 3 kilowatt per kg. So these are the small things we should understand. So it is, we are not studying ultracapacitor, when ultracapacitor, why ultracapacitor. These are the simple things you have to understand, and you don't read books for this. You just listen and put it in your mind, and that's it. Okay, so what to write in the exam, that's a different question, but why ultracapacitor, that we should understand. So it's a auxiliary or ancillary kind of a power source. Features of ultracapacitor. Yes, this is an exam question, so prepare this. So some 4-6 features are explained here. Double star slide. Previous slide was also features of ultracapacitor. This slide is also. So specific energy and specific power requirements can be decoupled. Important thing. So if there is a specific energy, the vehicle will go to the battery. If there is a high specific power, the vehicle will go to the ultracapacitor. It is possible. It is all by smart control, specific energy and specific power requirements, and supply demand thing. So vehicle is supplying, battery and ultracapacitor hybrid system can deliver it. Okay, so it can be decoupled. So if sudden ask is there, ultracapacitor automatically will sense that and it will come into action. If constant energy requirement is there, battery will keep on supplying it. So very important line, specific energy and specific power requirements can be decoupled. This gives an opportunity to design a battery that is optimized for specific energy and cycle life with little attention being paid to the specific power. So what happens if you are decoupling specific energy and specific power? So whenever specific power is required, it will not be taken from the battery. It will be taken from ultracapacitor. So the sudden high demand is not being put on the battery. Hence, the battery life cycle will increase. So in a combined energy power source, so this is the last line of the feature. We'll go for the next slide, that is construction. So in a combined energy power source, due to the load leveling effect, is very important. Load leveling effect. When to supply huge power, when to supply huge energy. This thing is actually sensed. So it's a part of BMS only. Okay. So energy management system in the vehicle. So due to the load leveling effect of ultracapacitor, the high current discharging from the battery and the high current charging to the battery by regenerative braking are minimized. So we are not expecting huge current charging of the battery or huge current discharge from battery. So battery is not a hi-fi device. Battery is not a very fast device. So some students are there who takes time to understand, and when understood, that knowledge goes forever. So battery is like that. It takes time to charge. It takes time to discharge. So for a longer period of time, it's like a kind of a steady person. For a longer period of time, if you are asking for some constant energy, battery is the person. So the ultra capacitor, the high current discharging from the battery and the high current charging to the battery by regenerative braking, both are minimized because there is a supporting system which is called as ultracapacitor, which is a power device. It can get charged very fast, it can discharge very fast. That means within a very small period of time, it can go to the full peak charge, and within a small period of time, it can discharge itself to the extent. So ultracapacitor is there so that the available energy, endurance, and life of the battery can be significantly increased. So this is what I was talking about by hybrid system. So battery alone can't do that, but yes, battery alone can be the main source or only source for electric vehicle possible because it's having high specific energy. Okay, so one discussion is there. What is the main requirement of a vehicle power source? Its specific energy should be very high. That is the only requirement. But if the vehicle is running on flat land, high specific energy wala source, no problem. It alone can handle the vehicle. But if the vehicle is expected to start at minus 25 degrees centigrade, or the battery is supposed to climb a hill, you are actually trying to do some stress testing on the battery, that how well it behaves in very demanding situations. In those cases, only battery is not possible. Okay, or in those cases, if you are trying to extract huge amount of power from the battery, which is actually energy device, in that case, what will happen is battery life will be reduced. So if for nominal operation, normal operation, use battery and keep a ancillary ultra capacitor with it, which will be helping it during the heavy power demand situations. So this is the background of ultra capacitor. We are going for construction. So we are finding that the double layer capacity. So this is very important slide. Prepare this. The double layer capacitor technology. What is the double layer capacitor technology? You can find out that there are two collectors. Okay, so there are two collectors here, and inside there is a electrolyte wala chamber. Okay, and they are separated by a separator. Likewise. So the double layer capacitor technology is the major approach. So it is not only a two plates and electrolyte. So there are double layer of electrodes and electrolytes you can find out. So these are two layers. Okay, so these are polarizing electrodes in both sides, and there are collector plates. So collectors are nothing but metallic plate kind of a thing. So first there is collector, then there is polarizing electrode, and after that there is coming the electrolyte. Okay, and electrolytes are actually having a separator because it is separating the positive and negative ions. You can check here like this. So double layer capacitor technology is a major approach to design the ultracapacitor. Here, two carbon rods are immersed in a thin sulfuric acid solution, separated from each other and applied with an increasing voltage from 0 to 1.5 volts. So voltages are applied, so you can find here there's a charge recombination taking place at the top. Okay, so these two layers are separated by this electrolyte, and we are applying voltage of 0 to 1.5 volt. So up to 0 to 1 volt, nothing happens in the electrolyte here. Whenever we are applying charge here like this between these two plates, up to 0 to 1 volt, nothing happens. But we go slightly above than 1 volt, that is 1.2 volt or something, bubble starts appearing inside this electrolyte. That means whatever water content is there, they are actually getting divided. Okay, so in that case, bubbles at the voltage greater than 1 volt, actually it says that electrical decomposition of water. So below 1.2 volt, the decomposition voltage, the current does not flow. But as soon as the voltage across these two plates are greater than 1.2, at that time there is a electric double layer which occurs in the boundary of the electrode and electrolyte. So you can find here, this is the electrode, and so here there is a separation of the water. All the negatives are getting stored here, and to balance it, automatically all the positives in this polarizing electrodes, they are getting stored here. So these are the positives. Okay, so as the concentration of these negatives are more, so how the concentration of negative occurs? Because we are applying the charge initially. As we are applying the charge initially, whatever is the electrolyte water, they are getting divided, and they are getting producing actually all the positives and negatives ions here, and all the negatives ions are stored here, and all the positive in the polarizing electrode is getting stored here. So these are the positive and these are the negatives which are actually getting recombined during the discharge process. So below 1.2 volt, so 1.2 volt and all these things are applied here. Below 1.2 volt, the decomposition voltage, so 1.2 volt is called as decomposition voltage. The current does not flow, but electric double layer occurs at boundary of electrode and electrolyte above that 1.2 volt. And the electrons are charged across the double layer. So these are electrons which are charged across the double layer for a capacitor. An electrical double layer works as an insulator only below the decomposition voltage. So below the decomposition voltage of 1 volt or 1.2 volt, nothing happens. There is no charge storage. But as soon as we are giving voltage greater than 1.2 volt, at that time first the electrolysis happens, then the negative gets stored here, positive gets stored here, and the positives are getting stored here. All the negatives in the polarizing electrode, they are getting stored here. And as the negatives are stored here in the electrode, so this is the boundary of the double layer. As a negative, to balance it, counter it, all the positive gets stored here, and this positive and this negative, they are actually going through the load when we are asking for discharge. So here below the electric double layer symbol is shown. So in between whatever big layer is there, rectangle, you can find it is nothing but the electrolyte layer. So separator electrolyte, it is here. Here there is a electrode, polarizing electrode and collector. Here also there is a polarizing electrode and collector. So this is the symbol of ultracapacitor which is shown below. Now how much is the stored energy? So you are finding that there are two plates which are separated by a electrolyte. So this is acting as a capacitor. Capacitor is given by C, capital C, and whatever voltage applied between the 2 points, two collectors or the two plates, whatever are there, that is given by V. So how much is the stored energy? So we know capacitor stored energy, so it is half CV square, evergreen formula. So C is the capacitance in farad, and V is the usable voltage in the volts. Now, operating principle of ultracapacitor. There are four statements. You have to understand all the four statements very clearly. So, E cap. E cap is how much is the energy stored in the ultracapacitor. So, first it will store energy. It cannot store power. It is actually storing energy, and at the rate it is storing energy is called as the power charging. So, E cap is equal to half CV square. We have seen. So, C is the ultracapacitor value, C, and whichever voltage we are supplying to charge the capacitor is given by V. So energy stored is half CV square, indicates that higher rated voltage is required for larger energy density in C. There is no rocket science. So more value of voltage you are using means the device will get charged to a higher extent. That means E cap will be more. So up to now, a capacitor rated voltage and aqueous electrolyte has been about 0.9 volt per cell. So this is a data you have to remember. How much is the V that we are given? So it is 0.9 volt with non-aqueous electrolyte. So there are two types of electrolytes. Solid electrolyte is also possible. So non-aqueous electrolyte means where there is no water there. So it is 2.3 to 3.3 volt each cell. So non-aqueous electrolytes are actually storing higher voltage. So it is 2.3 volt to 3.3 volt but for non-aqueous electrolyte. So these are the questions which might be asked in IEA. So please prepare. And for aqueous electrolyte, it is 0.9 volt per cell. This is the first statement. Second statement, what is saying is merit in using an electrolyte double layer in place of plastic or aluminum oxide films in capacitor. So we might use plastic or aluminum oxide film. We can use that, or we can use electric double layer. So sometimes we are generating capacitors with aluminum films or plastic, okay, a conducting plastic likewise. But instead of that, we are using a double layer technology. Double layer means first there is a collector, then there is a polarized electrode. So as we have seen in the previous slide, polarizing electrodes, and there is a collector, and there is same thing here. So there is a double layer technology which is specifically designed for ultracapacitor, so that it can supply more higher power to the devices, so it can save more energy and very fast it can charge or discharge. What is the merit using a double layer technology in place of plastic or aluminum oxide films in the capacitor? So what is the advantage? So that thing is given here. So still we are in the construction of ultracapacitor. It says that since the double layer is very thin, okay, as thin as one molecule with no pinholes. So pinholes actually kind of creating a short circuit. So there should not be any pinhole in the double layer. So since the double layer is very thin and there is no pinhole, the capacity per area is quite large, 2.5 to 5 microfarad per centimeter square. So this is 2.5 to 5 microfarad per centimeter square. That means every centimeter square is generating the capacitance of 2.5 to 5 microfarad. Okay, so centimeter square is nothing but the plate area. Okay, so that means you can imagine that it's a quite a big value of capacitance what this thing is actually creating. So creating a high value of C will actually increase the energy storage capacity by the ultracapacitor. So first they are saying how much is the energy stored in the capacitor. Second, they are saying what is the material used. So new material, new technology used is double layering instead of using plastic or aluminum oxide. And there we are finding that the capacitance produced is very high. And how much is that? 2.5 to 5 microfarad per centimeter square. Okay. So even if a few microfarad per centimeter square are obtained, the capacitor energy doesn't density is not large with aluminum foil. So that is another thing. So if C is not there, it cannot hold bigger charge density. So even if a few microfarad per centimeter square are obtained, capacitor energy isn't density isn't large with aluminum foil. So double layer technology actually generating high energy density. This is the bottom line. Whereas the plastic or aluminum oxide foil technology, energy density for capacitor is less. So to increase the capacitance value, activated carbons electrodes are made with very large area. We have seen in the previous slide. So there are polarizing electrodes, they are made by this carbon. Like surface areas of 1000 to 3000 meter square per gram. That means whatever electrode you are using, the weight of that thing is in gram, and that gram is converted to how much area. Okay, so 1000 to 3000 meter square per gram means each gram of this carbon material is generating 1000 to 3000 meter square of plate area. Okay, that means you can imagine how thin it will be. So that's why it is said that very thin electrode without any kind of pinhole, it is said here. So 1 gram of this carbon is converted to 1000 to 3000 meter square area. So 1 gram को तुम उतना flat कर रहे हो. Okay, so imagine how thin it will be, and that thin is actually kind of a collector of all the electrons or holes or whichever are the charged particles. So that's why they are saying this double layer is a very thin and it's having a capacity per area is 2.5 to 5 microfarad. Okay, so this is how thin we are making it. So the carbons of 1 gram is being thinned up to 1000 to 3000 meters square per gram. Last point, the energy density of these capacitors is smaller than the batteries. Okay, so energy density is less, but power that it can supply will be more. The typical specific energy of ultracapacitor at present is 2 watt hour per kg, which is only 1/20th of 40 watt hour per kg. Because the 40 watt hour per kg is the specific energy of battery. Okay, and the same thing in specific power by ultracapacitor, specific energy of ultracapacitor is 2 watt hour per kg. So compared to 40 watt hour per kg, ultracapacitor specific energy is 2 watt hour per kg. It is very less. That's what I told you in the beginning itself. Ultracapacitor is mainly for a power source, and battery is a energy source, because energy source should be having high specific energy, that is 40 watt hour. Ultracapacitor is having only 2 watt hour per kg. So which is the typical energy density of available lead acid battery? So lead acid battery is having 40 watt hour per kg. Nickel, cadmium, and lithium ion are having further high. So they are not even coming in any comparison with ultracapacitor, which is having very low specific energy. Okay, so we are not using ultracapacitor for specific energy, but using for specific power. Now is coming 2-3 slides which are having some little bit of equations. So they are not difficult. Okay, the same thing, half CV square is the main equation. So ultracapacitor performance is represented by terminal voltages during discharge and charge with different current ratings. So there are three main parameters. First is the capacitance of the ultracapacitor, uh, and how much maximum voltage it can store, VC. Second is the series resistance, RS, and third one is the leakage resistance, RL. So RL is the main culprit, and RS also. So there is a parallel resistance to ultracapacitor, and there is an internal resistance we have seen yesterday in case of battery. Same thing is there, RS, which is called as a series resistance. So you can find here this circuit, this slide is very important. So this VC, this is the voltage actually we are asking from the ultracapacitor. So this is the C value, and across this there is a RL. So leakage resistance appears in parallel with C, and series resistance which is there. So these RS and RL, externally they are not connected, they are not external thing, but they are actually are there. Okay, so you have to understand that. So automatically these are internal thing. uh, so parasitic resistance and all these things you have heard, leakage resistance, all these things you have heard. So whenever we are charging a capacitor of 5 volts, suppose we are giving 5 volt DC to the capacitor, it never get charged to the 5 volt. Maybe you can keep it for 10 days with 5 volt DC, but it will never go to 5 volt DC, because there is some extra, some recombination or some voltage drop across RS. So RS may be having a zero point 0.1 volt. So here you are connecting, so this is discharging voltage what they have shown here, but I'm talking about charging. So 5 volt you have connected, this capacitor voltage will never become 5 volt, maybe it will 4.9. Where is that 0.1 volt going? That 0.1 volt is actually across the series resistance. Okay, so this is actually some internal drop which happens in case of ultracapacitor equivalent circuit and all. So we can find it here. And one very important thing, whatever is the current given by the ultracapacitor, that is getting divided into IL and I. Okay, so ultracapacitor current is getting divided IL and I. So IC is equal to IL plus I. That you have to understand. Output voltage taken from the ultracapacitor is VT, and ultracapacitor stored voltage is VC. So whenever we are storing or charging the ultracapacitor, it is getting charged up to VC, and it is producing IC during discharge. IC is getting divided into IL and I. So IL is again produced flowing through the leakage resistance. Okay, and I is being given to the actual output. So I is actual current we are getting at the output, but IC is actually produced by the ultracapacitor. So IC minus I is equal to IL. Equivalent circuit, so the terminal voltage of the ultracapacitor during discharge can be expressed as VC minus IRS. So it is stored with VC, but we are getting VT terminal voltage as VT, and because some drop is occurring across RS. So if it is 5 volt charge voltage, we are getting 4.9 volt at the output. That 0.1 volt is occurring across the RS. Very important thing, the electric potential of the capacitor can be expressed as dVc dt. Okay, so we know that this is I by C or IC by C. Now I told you that IC is nothing but I plus IL. Okay, like this. And why is it negative? Because IC is a incoming current to this node. Okay, so it is dVc dt is equal to IC divided by C. This you have to understand, please concentrate. dVc dt is equal to IC by C. What is IC? It is the capacitor current, and C is the ultracapacitor value. Now IC is coming towards the node, IL and I are outgoing currents. So if IC is taken to be positive, IL plus I is going to be negative. Hence this negative comes. So it takes quite a lot of time to understand all these concepts. I'm explaining it. In books, it is just given. It is not explained. So please give time at a lectures to understand it. So IC is converted to minus of I plus IL divided by C. Here C is the capacitance of the ultracapacitor. So very important slide. Every small formula you should understand. So the leakage current is VC by RL. This is understandable. So this is the voltage across this VC, and this current is IL. So voltage divided by resistance is IL. This is understood. Ultracapacitor model you can find out. So this VC is actually related to minus 1 by RL is coming here. So this path, whatever is shown, is this path. Okay, IL is getting added to this point, and minus IC is related to RS. So you can find out this minus 1 by C. Okay, this is related to the this I which is going outside. So this is this part. Now at this point, IL and I are getting added. So this is nothing but this part. Okay, and we know that integrate. So what is the voltage across the capacitor? It is integration of I. So instead of IC, you have to write minus I plus IL. Okay, integration of minus I plus IL into dt. So that's why you are adding these two currents, I and IL. It is getting added here, and they are getting integrated. An integration of IL and IC. So the top one is IL, and the bottom one is I. So they are producing actually IC. So this IC is coming here after integration, and they are nothing but producing that VT. So what is VT? VT is equal to VC minus IRS. Okay, so here IRS is also said. This is the IRS part. Okay, whatever is the current, this part is getting added. So this I into minus 1 by C is here, and this minus VC by 1 RL is here, and this I into RS is going to the output. So this is the ultracapacitor model, and this is having the equation. So dVC dt is equal to IC by C, and we are actually substituting IC by I plus IL with a negative, because IC is incoming current, IL and I are outgoing current. Now you can divide this. So it is so there should come a minus here. So I by C and VC by CRL. Likewise. So performance of ultracapacitor, there are big equations, so don't worry, all these things will not be asked in the exam, but at least if you are designing sometime an ultracapacitor based system, this kind of formulas will be asked. So how much is the VC? So VCO, what is VCO? Is the initial charge, whatever was stored in the ultracapacitor. It is not ever completely discharged. So whatever was the initial charge minus whatever things are given to it. So this is the ultracapacitor terminal voltage at any time during discharge. So I is the discharge current. Okay. So this was the maximum stored charge at 0 instant of time, and this is the discharge rate. So discharge is happening through RL, through RS, all those things are there, and this is the voltage you are getting at the output. Okay, likewise. Now a very important graph in the right side. So this graph can be asked for discussion. What we are finding is x-axis is the discharge time. So how fast the ultracapacitor can give you output current. And this is a cell terminal voltage. Here if you are asking for 50 ampere current, this will give you, so starting from 2.5 volt. So all the graphs are starting from 2.5 volt. This is a graph that how much voltage it can give with how much current. So voltage multiplied by current is equal to power. So if you are asking, the voltage is so VCO is going up to 2.5 volt. So this VCO is 2.5. That means every time the ultracapacitor is starting from initial voltage of 2.5 volt. But you are asking 50 ampere current. In that case, you are asking less current actually. So in that case, the voltage will drop like this, and all these are linear graphs you can find. But if you are asking 100 ampere currents, in that case, it will discharge very fast, and within 60 seconds, the ultracapacitor will discharge. So see that it can give supply output, very high current it can give, but what is the time in second, discharge time? Very important graph. Okay, remember. So within 2 minutes, so it will only supply for 2 minutes or 120 seconds with 50 ampere current. Just imagine. So it started with 2.5 volt, 50 ampere. So 50 ampere into 2.5 means how much? Almost 125 watt it is supplying. But it can supply it for only 2 minutes, and it will continuously discharge. So this is the working range, and it is saying that this is a Maxwell 2600 farad. This is a company of ultracapacitor most widely used. So this is a discharge characteristic of Maxwell 2600 farad ultracapacitor, and is shown here at different discharge rates. The voltage linearly discharges with the discharge time. Okay, and remember that 120 seconds. So within 2 minutes, completely it is getting discharged. So at a large discharge rate, voltage decreases much faster at a smaller rate. So you are finding that if discharge rate is very fast, that is 100 ampere you are asking for it, within 1 minute the whole ultracapacitor will get discharged. If you are asking for 200 ampere from it, it will supply, that is the biggest thing, it will supply 200 ampere for some high power application, but within 30 seconds it will discharge, and again you have to recharge it. And for recharging you can use a high specific energy device which is called as a battery. So very important slide, a very important graph. At a large discharge rate, the voltage decreases much faster than the small rate. Now there is a charging efficiency given by eta d, Vc capacitor voltage minus Rs into It, and charging is Vc by Vc minus Rs into It. So there are Vc by Vt or Vt by Vc, terminal voltage to capacitor voltage. So whenever you are talking about discharge, okay, so terminal voltage is output, capacitor voltage is the input. When charging, capacitor voltage, because capacitor is getting charged, so how much is the capacitor voltage? This is actually you are measuring, so this is the output, and terminal voltage. So in case of charging, from the terminal you are giving the supply in, and in discharge you are taking the supply out from the terminal. So in case of charging, terminal voltage is higher, but the charging has to happen through Rs. Hence whatever Vt you are giving, the whole thing is not going to Vc. Okay, some loss is there at Rs. So that's why they are saying that different values of Rs, actually they are going to affect the both charging and discharging process. So here you can find x-axis is terminal voltage, okay, and y-axis is discharge efficiency. So this is a discharge characteristics, and we are finding that x-axis is terminal voltage. That means how much voltage we are obtaining at the output. So here it is the discharging mode. So It is equal to 50 ampere, It is equal to 100 ampere. So you are finding that if discharge is happening very fast, that means you are asking for 600 ampere. In that case, efficiency is maximum how much? 80%. So check the lowest graph. X-axis is terminal voltage. So how much is the terminal voltage? If you are asking for 600 ampere, automatically the terminal voltage will be 80%. So if you are talking about a Maxwell 2000F, it is having terminal voltage of 2.5 volt. You are finding here Maxwell 2600F is having terminal voltage of 2.5. But if you are talking about huge amount of current you are asking from it, 600 ampere, it will not be starting from 2.5 ampere volt. It will be starting from 80% almost of 2.5 volt. That means initial voltage when Vc should have been 2.5, it will not be 2.5, it will be 2 only. So 80% almost of 2.5 is 2. So if you are asking huge current from the ultracapacitor, it will not start from even its peak voltage. But you are asking smaller current, 50 ampere, it will almost start from 2.5 volt. So that is what they are saying. The discharge efficiency, it varies depending on how much current you are asking from it. So you are asking too much current from the beginning itself, its output voltage will be less. So you can check this voltage. So 200. If you are asking for 200 ampere current from the beginning, it will be starting from around 90 or 90 or 92%. That means almost 22 2.2 volt. Okay, but you are asking huge amount of current 600 ampere, it will start from 80%. That is almost 22 2 volt it will start from. So this initial starting voltage Vc from where the capacitor will start discharging, that depends on how much current you are asking. So equation indicates that energy loss in ultracapacitor. So this equation is caused by Rs. So more is the Rs, charging voltage also will be less, discharging output voltage Vt also will be less. So the series resistance is the main culprit. The efficiency decreases at a high current rate and low voltage. That is given here. Okay, so efficiency decreases at high current rate and low voltage. So more is the discharge current you are asking for it, less voltage you are going to get. So thus in actual operation, the ultracapacitor should be kept in its high voltage region for higher than 60% of its rated voltage. So we should not try the ultracapacitor with less than 60% of its rated volt. That means too much current we should not ask from the ultracapacitor. That is very important thing. So ultracapacitor efficiency, stored energy is given by EC half C Vc square. So Vc is the capacitor of the voltage. So Vc is the cell voltage in volts. At its rated voltage, the energy stored in the ultracapacitor reaches its maximum. Equation above indicates that increasing the rated voltage can significantly increase the stored energy. So VCO increasing, energy stored will get increased. In real operation, it is not possible to completely utilize the stored energy. So if we are saying that 2.5 volt is there, you cannot say I will discharge it to zero, or whatever is the energy stored in the capacitor, I will extract it completely. Not possible, because there is something which is called as SOE, that is state of energy. So ultracapacitor is usually given a bottom voltage CV. So even if it is starting from 2.5 volts, suppose it is say that bottom voltage VCB is suppose 0.5 volt. So it will start discharging from 2.5 volt with whatever current you want. But zero point 0.5 volt, if the voltage comes below 0.5 volt, it is not going to discharge anymore. So that is actually given by VCB. So ultracapacitor is usually given a bottom voltage VCB, below which the ultracapacitor stops delivering energy. That means you cannot totally extract all the energy from ultracapacitor. There is a lower voltage below which ultracapacitor will not deliver. Consequently, the available energy for use is less than its fully charged energy. So there is something called as utilizable energy. Okay, that is given by EU half C VCR minus CB square. What is CB? CB is the bottom voltage. And what is CR? So CR is the maximum whatever you can utilize. So usable energy in ultracapacitor is given by SOE, so state of energy. Okay. This is a ratio of energy in the ultracapacitor at a voltage of VC to the full energy at fully charged voltage. So VCR is expressed as, so SOE is equal to C VC square, so VC divided by VCR. So what is VCR? So it is saying that the consequently the available energy for use is less than its fully charged energy, which can be expressed as this equation, where VCR is the rated voltage of the ultracapacitor. So one is full voltage VC, what is the maximum, and another is the rated voltage. So ratio of full voltage and rated voltage is giving you the state of energy. This is the formula. So numerical can be asked on this SOE formula and energy stored in ultracapacitor formula. So here it is given. So this is a graph which is between cell voltage and SOE. You are finding that below this, the ultracapacitor is not going to give any kind of discharge. So various ultracapacitor technologies, according to the goals set by US Department, is a very important dictum. The energy for the inclusion of ultracapacitor to near-term specific energy, it should exceed 5 watt-hour per kg and 500 watt per kg respectively. That means we want, or US Department of Vehicle Energy, they have said if you want to include ultracapacitor as a vehicular component, in that case it should be having specific energy of 5 watt-hour per kg or specific power of 500 watt per kg respectively. But while the advanced performance, it should be 15 watt-hour per kg and 1600 watt per kg. But none of the available ultracapacitors can fully satisfy these goals. That means 5 watt-hour per kg specific energy, 500 watt per kg specific power, or for high operation 15 watt per kg or 1600 watt per kg. So 15 watt-hour per kg and 1600 watt per kg. So this K should not be there, it should be par. Okay. So we are not at all close to all these values, whatever is mentioned by US Department of Energy. Nevertheless, some of the companies are actively engaged in the research and development of ultracapacitor EV and HEV application. Maxwell Boost Cap 2006F, okay, which is having a voltage of 2.5 volt DC, and integrated modules 145F at 42 volt. So these are different other modules. 435F farad. So these are capacitors at 14 volt are in production. So there are three Maxwell farad things are explained here. So one is 2600F 2.5 volt, one is 145F 42 volt, another is 435F 14 volt. So there are three different things which Maxwell company is producing, and here are the different ultracapacitor technologies which are available in market. So you can see this chart, and what is the capacitance, what is the resistance, series resistance. So you can find out how much is the series resistance. It is 0.7, 10 ohm and 4 ohm likewise. So how much is the volt continuous peak? So voltage is 2.5 and peak is 2.8 volt. So voltage is 42 and peak can go to 50. So likewise, so these three modules are actually compared, and their volume, weight, operating temperature. Operating temperature you can find minus 35 to 65 degrees centigrade. Leakage current all these things, 5 milliampere, 10 milliampere, 10 milliampere. So you don't have to remember this, but what I request you to do is at least see this table and understand what are the range of the specifications. That means how much is the leakage current. Does it go in milliampere? We don't know. Okay, so whatever are the leakage current, whatever are the rs value, what are the temperature range, the nominal values you should know. That's why you should see this table and comparison of ultracapacitors. So we have completed the ultracapacitor thing. So main things are what are the features, why ultracapacitor, where is the scope, so where can we use ultracapacitor, features, construction, what are the performance formula, and what are the technologies, and who is defining the technology, how much is the requirement given by US Department of Energy. So somebody decides some requirement, and after that the design and R&D starts. Okay, so this is the requirement posed by US Department of Energy, and depending on that, the Maxwell company is producing their ultracapacitors. There are three different ultracapacitors: 2600F, 145F, 435F, and these are various ultracapacitor technologies which are available in the market. More are there in the market because there's a book written almost 10 to 15 years back. Present ultracapacitor technology you can find out. So this is an ancillary or auxiliary power energy unit that you have to understand. And this is not only this ultracapacitor cannot drive a vehicle. This is just for the peak requirement supply, peak demand supply. Like we keep a separate fund for Diwali. Okay, we don't use that Diwali fund every day. Every day we are using our salary to run our home, but some separate storage we are keeping for big occasions, maybe medical, maybe occasions, celebrations and all. So ultracapacitor is like that. Whenever the special case comes, it supplies huge amount of power in very short span of time. So we have seen that within 1 or 2 minutes, the ultracapacitor gives huge current and totally gets discharged. So I'll be uploading all the slides and everything, and I'll try to upload all the OBA question by this weekend, and you please answer and submit by next week. That's all from my side now. Thank you.